Chapter 20 is about conventional energy alternatives. The case study is about Sweden and trying to phase out nuclear power. All right, on 554, we have a couple of lists that you actually need to know and memorize these two lists. So you need to know the difference between energy and electricity. So energy is everything that we use for energy. For transportation, for heating, for cooking, for electricity. So everything combined, number one would be oil. Number two is coal, then natural gas, and then biomass. You need to know those four in order. Now, electricity is just electricity. Energy includes electricity, but if you're just talking about electricity, coal is king. So number one is coal, then natural gas, then hydroelectric, and then nuclear. Turning the page. Page 566, let's talk about nuclear power here. So these are the top producers of nuclear power. The United States actually produces the most nuclear power. We just don't think about it because it's only about 20% of our total electricity in the U.S. But because we're a large nation, we do produce a lot of power. So you can see here that we produce 102 gigawatts of power. And France is number 2. But we say France leads the world in nuclear power because it makes up the highest percentage of their own electricity. So for us, it's 19%, almost 20% of our power, but for France, those 63 gigawatts actually produce about 75% of their power in France. Now, I was recently in France, and I did see a lot of wind power, so they are trying to add to their electricity portfolio with some more renewable type sources as well. Okay, so what in the world is nuclear fission? How do we get power from a nuclear power plant? Well, you can see up here that we split uranium, in particular the isotope uranium-235, and we bombard it with a neutron to split it in half into two other atoms. And in the process of splitting it, it releases huge amounts of heat, so energy in the form of heat. And that heat is used in the same way coal is used to heat up water, to create steam, to spin turbines. So you do need to know specifically that it is uranium-235. And we bombard it with a neutron. It causes other free neutrons, which then hit other uranium atoms. Once you start a nuclear chain reaction, you can't stop it because the neutrons just basically keep going and going and going and going, and we consider this a positive feedback loop. You can see here on the next page a diagram of a nuclear power plant, and again it's the same kind of concept. So instead of having coal here that we light on fire, we have nuclear rods, and these nuclear rods keep reacting, and eventually they run out. We call them spent nuclear rods, but in the meantime they're going to boil this water, and the steam spins the turbine and releases electrons in a generator. And then we have to cool the water back down before we reuse it. So we can reuse the water, but we have to cool it down first in cooling towers. Sometimes we cool it in a body of water like a lake or an ocean, and that can cause thermal pollution, which is not good. Okay, so you need to know that mined uranium comes out of the ground. A lot of our uranium actually comes from Nevada and was mined by the Navajos back in the day. So we have to enrich it to uranium-235. So it comes out as 238, and we enrich it into 235. And then we make it into these little pellets, and then the pellets go into fuel rods. And then the fuel rods in a nuclear power plant are stored underwater to prevent explosion. and the water cools them down to prevent explosions, and so we have to keep pumping in cool water and pumping out heated water, and pumping in cool water and pumping out heated water. And one of the problems with the Fukushima nuclear disaster in Japan was that the tsunami took out the pumps that pump the water in and out, and so the reactor cores heated up too high. So we also contain it in cement and steel walls to prevent leaks. And also, if there is an earthquake, then hopefully the uranium is contained within that steel and concrete. Doesn't always work, but that's the idea. Oh, and you can see under the sticky note a picture of the water surrounding uranium fuel rods. All right, you also need to know on 558 what a half-life is. So a half-life is the time it takes for half the atoms to give off radiation. And so for uranium-235, the half-life is 700 million years. So that's kind of a problem in terms of once we have created these nuclear fuel rods, they don't go away very easily. Once we're done with them and we can't use them anymore at a nuclear power plant, then what do we do? Now, the positive part of nuclear power, and it might be a stopgap situation for climate change, is to do more nuclear until we develop other alternates, because it has no air pollution nor any greenhouse gases, and so this is a good part of nuclear power. It's not all bad and it's not all good. It's somewhere in between. So this is an important part. Okay, down here is nuclear fusion. So to fuse something together is to put it together and make it stick. So the power of the sun basically takes atoms and they fuse them together. So two hydrogen fuse together to create helium. And we don't know how to do this. If we did know how to do this, that would be all the energy we would need on the planet. But we don't know how to do this yet. Now, there's a lot of scientists trying it, and we're getting kind of close, but right now this is still something that we know happens on the sun, but we don't know how to do it here on the Earth. Okay, so we've had some nuclear problems. So the first one was 3 Mile Island in the US, and this was back east, and it was a meltdown. So the official word from the US government is that there were no deaths from 3 Mile Island, although there is some evidence now that there might be some higher rates of thyroid cancer 30 years later after 3 Mile Island in that vicinity. So it's back east around Pennsylvania. And then the second one was in the 1980s. It was in Chernobyl. At the time it was the USSR, so we call that the Soviet Union. But when the Soviet Union broke up in the early 90s into Russia and other various countries, Chernobyl ended up in the Ukraine. So it's in the country of the Ukraine right now. So there was an explosion and radiation spread all over Europe. And you can see the map down here where the radiation spread. And that was just kind of where the winds took it on that particular week. So some places got more radiation than others depending on how the winds blew. This country, this is like Albania, and it's a very secretive location at the time, and so there was no data because they didn't provide any. It's a very secretive country at the time that this happened. And then the third nuclear one was more recent, just a few years ago in 2011, in Fukushima, Japan. An earthquake occurred, then a tsunami. So the tsunami, you can see here the tsunami right here towards the Fukushima reactors coming in. Basically, it knocked out the generators. They couldn't cool it down. It caused explosions and a lot of radiation exposure. So in particular, you need to know that radiation causes thyroid cancer. Don't ever just write cancer, but on FRQ, write in particular thyroid cancer. All right, so what happened at Fukushima? So this is a reminder of plate tectonics. So we have a convergent plate with subduction. So one plate is subducting below the other here off the coast of Japan. So the plates are like right here off the coast. So what happened is one slipped below the other and caused a displacement of water right here, which caused the tsunami. And that's just a reminder from chapter 2 when we learned about plate tectonics. And here on page 562, go ahead and take a look. So a thyroid gland is actually in the throat area, and so this is a kid after Chernobyl being treated for thyroid cancer. It's very sad. All right, page 564. So how do we store fuel rods? Well, these are all spent fuel rods being stored at their location. So currently we store the spent fuel rods at each power plant, has a storage facility. Long-term storage is currently, by Congress, still planned for Yucca Mountain, Nevada. Why they chose Yucca Mountain, Nevada is because it's away from large population centers. So it's not near Vegas and it's not near Reno. At the time they chose this mountain, it was not considered seismically active, but there is some concern that it might be. And then they want to store it deep underground in tunnels. There is nothing being done for Yucca right now. It's kind of halted, but there still is no other plan on the books to resolve our ongoing spent nuclear waste issue in the U.S. You can see here that Nevada has opposed Yucca Mountain because Nevada has no nuclear power. So they're being asked to take the entire country's nuclear waste to their state, and so they don't like that very much, and I don't blame them. So here's the proposed plan that it would be shipped way underground and stored here in Yucca Mountain. But again, it's not currently the plan. So currently waste is stored at each location, but the long-term plan is to store at Yucca Mountain. But I don't know if that will ever happen. It's kind of on hold. Okay, the next source of energy on page 566 is bioenergy, and sometimes we call that biomass. So there are a lot of sources of biomass here on page 567. Basically, it's anything that's from a living thing that we burn. So mostly trees, but it could be charcoal, which is burnt trees that we use to cook with again. Some people take manure like cow patties and they burn those. They did this on the Oregon Trail a lot. They found buffalo patties, poop, and they burned those to cook their dinner because there were no trees on the prairie. So how are they going to cook their dinner? So they burn those. In the United States, we grow a lot of corn for ethanol. In Brazil, they grow sugarcane for ethanol. And then other sources, cooking oil for biodiesel. And then we can also use crop residues, corn stalk. We can burn those at power plants for electricity. Same thing, we burn coal, instead we burn crops. Now, it's not as much energy. Why do we like coal so much? Because there's so much energy stored in those bonds that we get huge amounts of energy and heat from burning coal as compared to these. But we can still burn all of these as well. Okay, so the biomass that's used for automobiles are called biofuels. The one that's most known is ethanol, although you could be asked about biodiesel as well. But ethanol is from corn in the US, and you can buy a vehicle called a flex fuel vehicle that runs on E85. So E85 is 85% ethanol and 15% gasoline. The problem with ethanol is that it's driven the price of food up because now you have competition between food and fuel from the same corn crop. Also, it doesn't really save very much. So a lot of people say, oh, grow more ethanol to solve global warming and burn our cars on ethanol instead of gasoline. The problem is that it doesn't really save very much in terms of CO2 and other air pollution emissions because growing corn actually uses a lot of fossil fuels in the production, in the pesticides that are used to grow it, in the farm machinery, all use fossil fuels. You also need to know that Brazil doesn't use corn, they actually use sugar cane for the same thing.